To turn on the LSM 980, first turn on the components switch labeled number 1. Second, turn on the computer at label number 2. For microscope controls, you have the XY joystick to move the stage up, down, left, or right. The focus controls are the large knob for coarse focus or the small knob for fine focus. On the left side of the stand, the large knob is for coarse focus and the finger holes are for fine focus. The large black box is for environmental control. Please consult scissor staff for live cell imaging or the appropriate temperature for ARI scan. For fixed imaging, you may access the stage here by opening the sliding doors. And below, you may open the small window for appropriate airflow. In order to place your sample on the stage, first lift back the condenser arm using the knob. Please be very gentle. Now you have room to place your sample on the sample holder. For ease of placing your sample onto the sample stage within the chamber, there is a flashlight knob on the top right. To place your slide on the slide insert, first insert your slide so that the cover slip is toward the objective. There are 2 side bars that adjust for the size of your slide. You may also tighten it with the 4 side screws. If you have a sample other than a slide, please consult scissor staff for the appropriate insert. The touchpad next to the keyboard also controls the microscope. From the home screen, you may choose your objective. On the right side, you have the same focus knobs, coarse and fine focus, as the microscope stand. For the immersion lenses, please choose the most appropriate immersion media. Room temperature oil, 30-degree oil, 37-degree oil, water, or glycerol. Each should have a plastic dropper. To add immersion media, please be careful and use 1 drop of oil directly onto the objective without touching. Please be careful not to add too much oil. Once you have added the oil and your slide to the stage insert, slowly focus the coarse knob so that the objective moves toward you until you see the immersion oil spread between the cover slip and the slide. Finish the fine focus at the oculars. After you have placed your sample, gently lower the arm back down. Turn off the flashlight and move to the software. To remove your slide, unscrew all 4 fastening screws. Gently pull apart the 2 arms and lift your slide. To clean immersion media from the objective lens, first, find lens paper on the counter. Use a single piece of lens paper. Place the lens paper over the objective and place your finger gently on the paper. Use a single pulling motion to remove the oil. Repeat if there remains oil on the lens. If you have an accidental spill or see excess oil that needs cleaning, please contact scissor staff for proper objective cleaning. Once the computer has started, after you've seen the Excel file open, please navigate to Zen Blue to run the microscope. You may find the Zen Blue icon here on the taskbar or on the desktop. Once you open, please choose Zen System. It will now take about 1 to 2 minutes for the software to fully launch. Once the software is open and you have calibrated the stage, you will see that the software opens to Locate, the first tab on the left. Now you will place your sample on the stage. Once you have done so, you want to send light to your eyes so that you can locate your focal plane. These quick buttons will be preloaded for you. You may choose Bright Field or DIC to find your sample by white light, or you may choose the fluorescence filter cube. Please note here below where you can see the filter cube that is chosen that there are only 2 cubes and they are multi-bandpass filters. Thus, you will see more than one color at your eyes. This is fine, just know that you will see more than one thing. For example, I could choose GFP. The light path will choose this filter. We'll turn on the GFP excitation to your eyes, and you may locate your sample. You may now switch to another. Once you are finished and you have found your sample and your focal plane, please choose All Off. This will turn off all the light to the oculars and to the microscope stand. Once you have located your sample under the Locate tab, you will move to the second tab, Acquisition. Now you have your sample ready, and we need to tell the software which fluorophores you have in your sample so that it can set up the light path appropriately, the excitation lasers and the emission. There are 3 ways that you can set up your tracks and your channels through the software. First, we're going to go over setup, smart setup. This is the most common and the easiest workflow. Click on Smart Setup, just 2 clicks below the Locate tab, and it will open a wizard for you. First, on the right, note if you are doing confocal imaging or Ariscan imaging. Please note that Ariscan will be taught in a separate video. For this example, we will use confocal, so please make sure that LSM confocal is highlighted in blue. Now, moving your mouse over to the left, under Add a Track, we're going to click the small plus sign. This will open another window where we will choose the fluorophores that we will image with for your sample. Down in the bottom half, under Dye Database, you could search the name of a sample, a dye, for example, Alexa, or you may scroll through to see them alphabetically. Most dyes that you will image with will be contained here. If they are not, please talk to Scissor staff. We can help you choose a similar one or help you add it to the database. For today's example, we will use 3 colors. We will choose Alexa 488 for something green. I will double click and it will populate it in the left window. Alexa 568 and Alexa Floor 633. Now I will close this second window and I can see my options here on the top left. Note that the colors are probably not as I would choose. So next to Alexa Floor 633 on the right, for the small white arrow, I can change the color. And I will change it to blue for today. Now, down below, for 3 or 4 color imaging, we have different options for how to set up our tracks and channels. In the first window on the left,
is called fastest. This will obviously be the fastest acquisition time, and you can see that by the gray bar notated as speed on the right. However, you can see our 3 fluorophores here. The bars below the middle line show you the crosstalk or the bleed through between the different channels. And you can see that there is some bleed through between these channels. The next option in the middle is best signal. You can see much reduced bleed through or crosstalk. However, it will be slower. In some previous versions or in other confocal softwares, this would be sequential imaging. Fastest is going to be simultaneous imaging. This will open another window where we will choose the fluorophores that we will image with for your sample. Down in the bottom half, under dye database, you could search the name of a sample, a dye, for example, Alexa, or you may scroll through to see them alphabetically. Most dyes that you will image with will be contained here. If they are not, please talk to Scissors staff. We can help you choose a similar one or help you add it to the database. For today's example, we will use 3 colors. We will choose Alexa 488 for something green. I will double click and it will populate it in the left window. Alexa 568 and Alexa Fluor 633. Now I will close this second window and I can see my options here on the top left. Note that the colors are probably not as I would choose. So next to Alexa Fluor 633 on the right, for the small white arrow, I can change the color. And I will change it to blue for today. Now, down below, for 3 or 4 color imaging, we have different options for how to set up our tracks and channels. And the first window on the left is called fastest. This will obviously be the fastest acquisition time, and you can see that by the gray bar notated as speed on the right. However, you can see our 3 fluorophores here. The bars below the middle line show you the crosstalk or the bleed through between the different channels. And you can see that there is some bleed through between these channels. The next option in the middle is best signal. You can see much reduced bleed through or crosstalk. However, it will be slower. In some previous versions or in other confocal softwares, this would be sequential imaging. Fastest is going to be simultaneous imaging, where we will image all tracks and excite all fluorophores simultaneously. Best signal will be sequential imaging, where we will image each one at a time so that the lasers are not firing simultaneously. This will separate the channels better, but it will be a slower acquisition. The third option here is called smartest. In this case, it is a line scan. This was previously called best compromise, which I think is a good way to think about it. Our speed will be in the middle, and we should have reduced but not non-existent crosstalk. In this case, we will put the Alexa 568 in a track by itself, and we will put the Alexa 488 and 633 together because their emission spectrum are further apart from each other. For today's example, I'm going to use best signal because it's a good way to walk through each track one at a time when we get into the acquisition. So I have highlighted best signal. I'm going to click OK at the bottom right, and the software will set up the light path and the imaging setup for me. There are 2 other ways that you can set up your imaging setup and your channels through the software. One is to open a previously acquired image that you acquired on the LSM 980. I have done so here, the second image. Make sure it is a CZI file and that it was acquired here. Then navigate over to the left again above the snap button and you will see a reuse button with a recycling symbol. If you reuse, it will take all the settings from this image and reload them under channels. Note that you will get a pop-up window asking you about the Z stack. Do you want to center the Z stack around the current focus position? This is generally fine because you have started a new imaging session. Click yes. And now your tracks are loaded here under channels. In this case, 2 tracks with 2 colors each. And you can see it has reused my previous settings for laser power, master gain, pinhole, and the settings under acquisition. The third way to set up your imaging setup and your channels through the software is here, the long button that says Experiment, located just above Smart Setup in the upper left. Open this drop-down menu and you will see 4 options, although 4 are for ArriScan, which we will discuss in a different video. There are 2 options here for confocal. Confocal 4-channel frame or confocal 4-channel line. These are intended for 4-channel imaging for the standard 4 colors. Something like DAPI around 405, something around excitation 488, something around red excitation 568, and something around far red excitation of 633. Frame will be a slower imaging and line will be a faster imaging. These may be appropriate, but if you have anything outside of these standard 4, we recommend Smart Setup or reuse. Once you have loaded your imaging setup and you have your channels and tracks, you will see the imaging setup here. We have it on the left under imaging setup. In this case, we have 3 tracks, 1, 2, and 3. Track 1 in this case is highlighted, the button is blue, and you can see more information about this channel here. The very skinny line here shows you your excitation laser. The red curve shows you the emission profile that will be collected. You can also see that here below, Alexa Floor 633 is the dye, and our emission range in this case is 411 to 695. Just to the right, you can see the channels here. Alexa Floor 633 is highlighted in blue, and below you can see that it is using the 639 excitation laser. Now we can navigate to track 2. This is Alexa Floor 568. On the right, you will see that we're using the excitation laser 561. And on the left, you can see the emission profile is 561 to 632. Track 3, Alexa Floor 488. On the right, you can see excitation laser 488. And on the left, the emission profile of 490 to 579. Note that these are all spectral detectors, so we have options. We can adjust this emission profile for each track. You may do this by grabbing the bars underneath. For example, we have 579 as our longest wavelength. I could adjust this smaller or larger depending on your fluorophore, your autofluorescence, or your specific sample needs. Once you have found your sample, found your focal plane, and set up your imaging setup and your channels, you are ready to see an image on the screen. Again, in the top left, we have 3 buttons for how you can scan your image on the computer screen. I want you to notice Live, Continuous, and Snap. Live is going to be a fast live version of your image. It will use the settings that you have here right now by default under channels. It will not use the settings under acquisition mode. So it will default to a 512 by 512 frame size, and it will maximize the scan speed. So it will be a fast scan. Also note that when you hit live, as I will do now, you will only see one color. This is different than the previous versions of Zen where you would have a split option and could see all three. Now we see one at a time. Alexa floor 488 was highlighted, so I see green. However, even while it's scanning in live mode, I may now click on 568 and it will switch. It takes 1 or 2 seconds for it to switch to another color. While in live mode, I may adjust my focus, and I may adjust my settings here. When I'm finished, I will click stop. The second button is for continuous. It is similar. It will be a continuous scan so that I can make adjustments, focus, or intensity as it scans. I will hit continuous. The difference now is that we can see all three. So once it has started, on the left side of the image, we have 2D or we have split. When I hit split, I can now see blue, red, green, and merge, my 3 tracks and my merge. I can adjust now. As you can hear, this is a slower scan because we have chosen the sequential or the best signal scan. So in this case, I would choose 1 track at a time by checking and unchecking boxes, hit continuous, and now it is easier to make my adjustments. But in continuous, it will use the settings that we see in acquisition mode. So once I have adjusted the frame size or the scan speed, that will be reflected under continuous. The third button is snap. Once I have optimized my image for each track, then if I want to snap an image, it will not be a continuous scan. It will just take the image once and then stop. You can hear the scan, channel 1, channel 2, and channel 3. And now the imaging stops, and I have my image that I may now save as a CZI image. Finally, when you get into a multi-dimensional image, so that could be a Z-stack, that is different Z slices, or a tile or mosaic scan, multi-areas in XY, or time series, multi-images in time, we will check this button, for example, Z-stack, and now we have an option here for start experiment. So if we want to acquire a Z-stack, we will optimize our channels, we will set our range for the Z-stack, and now instead of snap, we will hit start experiment, which tells the software that it is a multi-part image. Now we have an image on the screen. We have found our sample by our eyes, we have found a rough focal plane, and we have hit live or continuous. I will do live again. Here's our green image. I can navigate to red, and I can navigate to blue. If I use continuous, I can see all 3 channels. And this is my beginning image. I will stop so that I'm not hitting my sample with too much light. When we loaded our fluorophores and our information in the software under Smart Setup, there were default settings. Here, for each track, there are settings for each one. You can see a low laser power and a relatively low master gain. This will give us our baseline image, hopefully. Next, we need to optimize my image. As you can see in this example, green looks good, possibly a little saturated, red looks great, and I'm having trouble finding anything in the blue channel. So our next step is to optimize this image. Optimizing the image means a few different things. It means that we want it to be pretty, we want it to you want to see what you need to see, but it also means that we want it to contain the information you need to do whatever downstream analysis you're going to do. We want to optimize the acquisition of each pixel and make sure that we don't have too much or too little signal. There are a few different ways that we can look at this. One is to use the histogram that you see in the bottom middle of the screen. Right now, by default, we are using 8-bit imaging. You can see this in the middle here under acquisition mode. That means that every pixel in the image contains an intensity value between 0 and 255. This histogram gives a representation of that. Along the x-axis, we have the intensity of each pixel, 0 to 255, and along the y-axis, we have the frequency of those pixels. So, for ease, I'm going to turn the display of the red and the blue off, and here you can see the histogram of my green channel. You can see that there are pixels across the full range, but there are a lot of saturated pixels, and our eyes can generally see that. Now if we look at red, we can see a good separation. We're not quite at the 255 range, but we're close. And then obviously, if we look at our blue channel, we can see that our pixel intensities are very low and we have a lot of room left. Another way that we can look at this intensity range is just below the channels that I was choosing here, and it is called the range indicator. You may have seen this called high-low in other softwares. When I choose range indicator, any pixel that is 0 or background is now colored blue, and any pixel that is 255 or saturated is now colored red. So we have a quick visual representation so that we can see if we have used the full range. So as we expected and as we already learned from our histogram, our blue signal is very low. We need more signal. Our red signal is very close. We probably need just a touch more to fill the full histogram. And our green signal, 48, is saturated or has too much signal, and we need to bring that down. So as we see, we need more signal in blue, we're close in red, and we need less signal in green. There are 3 major ways that we can increase or decrease our signal, and we're going to do this one channel at a time. First, I'm going to go over these 3 parameters that we may adjust. These are in no particular order, and it will be a balance between all 3 of these things. Maybe we need to turn one up to get more signal and then turn another down to decrease our signal. One of the things that we can adjust to increase or decrease our signal is the laser power. Our first example here is for Alexa Floor 633 using the 639 nanometer excitation laser. And you can see that by the default of the software that we got through the smart setup, we are at a very nice low range of 0.2%. That's fantastic and should not harm our sample very much. Of course, we can turn the laser up and we will get more signal. The trade-off there is photo bleaching or photo damage. We can turn the laser up, we will get more signal, but at some point you will get photo bleaching of your fluorophore or phototoxicity of your sample. This is especially important for live cell imaging because of phototoxicity. With a fixed cell in low numbers, definitely below 1% or in the single digits, you should see minimal photo bleaching, but it is always something to keep in mind. So, for example, for 639, where I need more signal, I will hit live. And I can, for each of these boxes, I have several ways that I can increase these numbers. I can use the small arrows on the right, so I will click this up to 1%. I can also use this slider bar. I can also type numbers in the box. I will change this to 2.5%. And finally, I can click in the box and use the scroll wheel on my mouse. So you can see that as I increase the laser, I'm finding my signal in the blue channel. At the same time, because I'm in live, I will check my focus just to make sure I haven't gone out of focus. And be sure to stop the scan whenever you're moving to a next color or if it has been going too long. So our first option, or one option that we can adjust, is laser power. Turn it up, more signal, but your trade-off is photo bleaching and photo damage. Another parameter that we can adjust to increase or decrease our signal is here called the master gain. The gain is the detectors. This is what is detecting the light and collecting the photons. We can think about it like an amplifier. We will turn this number up, but at a certain point we will get noise from the machine. On this particular confocal microscope, the LSM 980, that sweet spot is around 800. If we can keep the master gain at 800 or below, we should have minimal noise. However, there can be occasions where you need to go a little bit above that. It will not harm your sample, but you may see some background noise. The third parameter that you can adjust to increase or decrease your signal is the pinhole. The pinhole is an iris that opens or closes to allow or reject out of focus light. As you close the pinhole down more, you are creating an optical slice where we are collecting the light, and as we close it down, we are collecting a thinner and thinner optical slice. There are several numbers here associated with the pinhole. Across from the pinhole on the right, where in this example it says 35 microns, this is the physical size of the pinhole in microns. Below that, however, we have another number in microns, in this case 1.4 micron section. This is the optical slice that we will be acquiring. There are two different ways that I like to think about how you can set your pinhole. One way is that you want the best resolution that you can get, and in that case you want this optical slice to correspond to something called 1 area unit. You can see that here, and over on the right I can click 1 AU and it will hold and highlighted in blue, and it will set the pinhole so that I am maximizing the resolution available for this setup. Now this includes a few different parameters. It includes your objective lens and, more importantly, the numerical aperture of your objective lens, but it also includes the wavelength. Another way that you can think about how to set your pinhole is that you know what you want your optical slice to be. So for example, you have a 30 micron piece of tissue. You may not want to take a slice every 0.5 or 1 micron. It would take a long time and it could be overkill. So you can think about this optical slice corresponding to the structure or the object that you want to see. So if you have a nucleus or some other organelle that you know is 1 or 2 microns, you may not need your pinhole or your optical slice to be smaller than that. So as I mentioned, the 1 area unit calculation depends on the numerical aperture of your objective, but it also depends on the wavelength. So in this example, I'm on Alexa Floor 633 and it tells me that 1 area unit equals 1.4 microns. If I now navigate to 568, you can see that that number is 1.2 microns. And if I navigate to 488, that number is 1.1 microns. Important note, just here under your channels, under the little settings icon, I can click on this pull down and choose select all. Scroll down a little bit and I can see all of my tracks together. So in this case, I can see that for 633, I have a 1.4 micron section, 568, 1.2, and 488, 1.1. Importantly, we don't want to acquire a different optical slice for different colored tracks. For example, we don't want to collect 1 micron in green and 1.5 microns in red. These would not match. We would not be collecting the same part of your sample. The 1 area unit calculation tells you the optimal place to be to maximize your resolution. So importantly, if we change this optical slice to be below 1 area unit, you will not add enough resolution. You will lose light. That is why we recommend staying around 1 area unit or larger. So because we don't want to go below 1 area unit, and because the calculation depends on the wavelength, generally we are going to match the optical slice to the longest fluorophore wavelength. So in this case, 633 is the longest, and you can see that it has the largest optical slice, 1.4. So in this example, where I want to be close to 1 area unit, and I have 633, 568, and 488, I will make all of the optical slices match 1.4 micron section. I will do that manually. 633 is here. Navigate down to 568, and I will increase this to 1.4. 488, navigate, and increase this also to 1.4. So for the example where you have Alexa Fluor 633, Alexa Fluor 568, and Alexa Fluor 488 on the 20x lens, where you want to maximize your resolution in Z, the optical slice would be 1.4 microns for each track. Now that we know there are 3 major ways to increase or decrease your signal, the laser power, the master gain, and the pinhole, we're going to walk through this setup one by one with each track independently. I'm going to start again with continuous so that I get my baseline signal on the screen. There's my blue, red, and green. I will hit split to see where I am. And I'm going to go ahead and hit stop. All I wanted to see was my baseline signal. As we already saw, we need more signal in blue, we might be okay in red, and we need a reduced signal in green. Because I want the pinhole to match across all tracks, across all fluorophores, I want to start, or the best idea is to start with the weakest channel. Then, if I need to open the pinhole, to accommodate, in this case, the blue or 633 track. The others have plenty of signal and will be able to accommodate that larger pinhole by reducing the laser or gain. So in this example, I'm going to go through one at a time and optimize the laser, the gain, and the pinhole, and I will start with the 633 track. So in this case, I think it's easier to uncheck the other 2 tracks. So I'm only going to deal with 1, and I'm going to use the live button because it will be a little bit faster. So I have 633, I'm going to hit live. And now I don't have much signal, so where should I start? I could increase the laser. Remember, the trade-off is photo bleaching. I could increase my master gain. I could get noise above 800. Or I could open the pinhole and acquire a larger optical slice. There are many different reasons that have to do with your sample and your experimental goals that would dictate which of these you adjust first. But let's take a look at the numbers and see what makes sense here. In this case, my laser is very low, so that's not a bad idea. But note that my master gain is only at 650. And I told you that you can go to about 800 without any noise. So in this case, I believe this is a good place to start. So I'm going to hit live. Again, I could use the slider bar or the arrows. I'm going to just change 650 to 750. And let's see if we have a signal. I see a little bit here. Now I'm going to focus, make sure I can find my sample. So we still need a little more signal. I'm going to change this to 800. You can also, if you're having trouble with the focus, you can adjust your display. I could use min max or best fit, just so that I can focus and know that I'm in the brightest plane. There's our brightest plane. Now I want to make sure to reset this. And so now, here's a good question. I've already taken my master gain to 800. I would like to stay there. I could open the pinhole to get more light, or I could increase the laser power. Again, this depends on your sample and your imaging goals. If we really want to maximize or optimize the resolution in Z, I would like to keep the pinhole where it is. And because the laser is really low, that's where I'm going to start for this example. So again, back to live. I'm only at 0.2%, so I'm going to try 1%. And now is a good time to use the range indicator tool again. So when I hit range indicator, I want to see if I can find just a few red pixels to know that I am just nearing the saturation point. I see just a couple. And again, a little bit of red or near saturation is a subjective call. You want to make sure that you're thinking about what structures in your sample that you are most interested in. So I'm going to hit stop. For this example, if I was interested in this brighter region here, this may be too much signal because I have a good bit of red pixels. If I was interested in these smaller rings, then I might need to sacrifice this area to get this particular region on scale. For this example, I'm just going for an overall little bit of red. So I'm actually going to bring this back down just a little bit. I'm at 1.5 laser. 1.2 looks pretty good, just a few red pixels. Okay, so let's revisit where we landed for this 633 track. We have our laser at 1.2%. We have our master gain at 800, and we were able to keep our pinhole at 1 area unit, which in this case equals 1.4 microns. Now remember, we set this before looking at all 3 tracks together. For setting your laser power, we want to talk about upper and lower limits. We suggest that you not go below 0.2%. Consider that the floor. The 405 laser will actually not let you go below 0.2%, and it's a good idea for the other lasers as well because the laser may not be as stable at very tiny amounts. For an upper limit, this is a newer system with new state-of-the-art lasers that are all solid-state lasers. So thus far, we have seen that we have been able to keep the laser power in the single digits. So I would consider that the suggestion for now. If you can keep your laser, for each laser, in the single digits and at 0.2% above or above, those would be the ranges to aim for. Now that we are pleased with our first track, in this case Alexa Floor 633, which was our weakest track, we're going to navigate to the middle one, which was red, Alexa Floor 568. Importantly, now that we are satisfied with our pinhole for this track, we will not touch the pinhole for the remaining 2 tracks because they are brighter and will be able to accommodate this 1.4 micron section. So now I have unchecked 633 and I have checked 568. Make sure you also click here to highlight that track so that we have the settings for that track. So just as before, I'm going to hit live. I'm going to check my focus. Importantly, for each track, we want to do this optimization on the brightest plane. If we're going to do a Z stack, which we will in a few minutes, we want to make sure that we have accommodated all the different Z slices. If we were not on the brightest plane, we step up in Z, we could now be saturated. So we will check our focus for each track. Okay, using live, again, we're going to use our range indicator, and this one looks really close. I can see just a few red pixels. we could probably bring this down just a touch. So again, we have our 3 options, but we're not going to touch the pinhole because we set it on our weakest channel. I just told you, or previously told you, that 0.2% laser power is our floor for laser power. And so now we're just left with one option. So we're going to use the master gain to bring our signal down just a touch. So I'm going to hit live again. I'm going to hit range indicator again. I'm going to click in the box, and I'm just going to scroll down a little bit till I see this reduced. So I would say that looks pretty good. Let's go with 640 for our master gain for red. One more time, I'm going to check my focus, just make sure I didn't miss something really bright. But this looks good. I'm going to hit stop so I don't hit my sample with any extraneous light. So let's look at these settings again. Our laser power is at 0.2%. That's fantastic. Our master gain is at 640. That's well below the 800 limit we discussed. And then we kept our pinhole as we set across all 3 channels to 1.4 micron section. Okay, now we're going to repeat this process for our 3rd and remaining track. I'm going to uncheck the red. I'm going to check the 488. Again, I'm going to click on this side so I have the settings. Same thing, I'm going to hit live, range indicator, and now we have way too much signal. So again, we have 3 options. We'd rather not touch the pinhole because we've set it for our other 2 tracks and we're happy with the 1.4 micron section. In this case, we don't want to touch the laser power either because we're already at 0.2%. So again, we're going to adjust to get our signal down by decreasing the master gain. And it may seem like we're not helping our sample much, but what we're doing is getting our image on scale. In this case, there's a lot of saturation and we are unable to distinguish many of these structures. So we're improving our image by optimizing the dynamic range of this image. So again, I'm going to use live. I'm going to use range indicator, and I'm just going to start by reducing 650 to 600. That helped a little bit. I'd need to reduce it more. Let's go to 525. And now we're getting close. I'm going to check my focus again. Make sure I'm on the brightest plane. And I'm going to bring this down even more till I have just a little bit of red. I think that looks pretty good. And so stop. Let's revisit these numbers. For 488, we have our laser at our bottom limit of 0.2%. We have our master gain well below our 800 limit at 505, and you can see just a few red pixels. And we have our pinhole set so that our optical slice remains at 1.4 microns, which is what we chose across all 3 tracks, 488, 568, and 633. And if you look closely, you can see that we have a lot more information in this green channel now, where we can see these individual rings and get a better idea of their size that we could not see when this particular track was saturated. Now that we have optimized all 3 tracks, let's take a look one more time. I'm going to check all 3 tracks. Again, over just to the right of this at the settings icon, I'm going to select all, and I can take a look at all the settings together. So 633, 1.2% laser, 800 gain, 1.4 micron optical slice. Track 2, 568. 0.2% laser, very low, 640 gain, and again 1.4 micron optical slice. And 488, again 0.2, very low laser, 505 gain, and finally 1.4 micron optical slice. So these are all well within the ranges that we've talked about, somewhere between 0.2% and 9 or 10% maximum for your laser. Master gain at 800 or below. and pinhole optimized for your particular sample, but importantly, our optical slice matches across 1, 2, 3 tracks. I have rechecked all 3 tracks. I'm going to hit continuous so that I can see all 3 and see my improved image. Stop. Over here on the left, I'm going to hit split so I can see all 3, and you can see much improvement in this image where I can see individual structures. Now, as we saw with the range indicator, I mentioned that we want a few pixels, or we want to see 0 indicating the background, and then a few pixels of red indicating 255 or saturated. The digital offset, which is a setting you will also have for all 3 tracks, controls the amount of background. In this particular software and with these much more stable detectors, we leave the digital offset at 0 for each track. So you may leave that at 0 for each one. Just below that, you will also notice digital gain, and we can leave that at 1 because that is a digital boost to your signal that we're not going to use at this time. Now that we have optimized each track as we have done, if we would like to take a single image, we are ready to do so. So if you remember, we're going to use the snap button here. I'm going to hit snap. Track 1, track 2, and track 3, and it will stop on its own. And now I can take a look at my image as a merge or as a split, and now I'm ready to save this image. Please note that anything, any of the windows open here that have the little orange pencil mean that they have not been saved. I'm going to go ahead and file save as CZI. You always want to save in the CZI format. That's the newest Zeiss format, and you want to save a copy of this so that you have all of the metadata associated with that image. As I mentioned, you want to save the CZI file so that it contains all the information that was set as you acquired this image. You can see that here in these tabs, these vertical tabs along the left side of your image under Info. You can see all the information about how we acquired this image. You can see the time. You can see that we had 3 channels. The scaling is here. We will demonstrate a scale bar later. So far, we've only done a 512 by 512 frame size, 8-bit. If you scroll down below, importantly, you can see the objective that we use, and you can see all this information that we just spent time setting up for each track. So for example, track 1 is a 639 laser at 1.2%. And then down below, you can see the detector gain was 800. And you can also see the pinhole was set to 1 area unit. Next, we will show how to acquire a Z-stack, a series of optical slices in the Z dimension. As noted at the beginning, the first step will be to check Z-stack on the left under Smart Setup. This will activate the Z-stack window. Navigate here under Channels and scroll down to find the Z-stack window. You can see that the Z-stack window gives you a little cartoon of how the Z-stack will be acquired. The objective is below your sample, and we will set the first slice to be closest to the objective and the last slice to be the farthest from the objective. This allows the objective to step up in Z so that it is fighting gravity. In order to do this, we're going to utilize the fine focus that is on our touch pad. We will choose whichever channel is important for you to see the top and bottom limits of your sample. In this case, these are similar. So we're going to move the objective down and hit set first. on the Zeiss microscope, moving the focus toward you moves the objective down. I'm going to choose the 488, a green channel. I'm going to use live. I only need one track at a time. I'm going to use the fine focus on the touchpad, and I'm going to slowly come toward me until I'm just a little out of focus. I'm going to click set first, and it will record that Z position. Now I'm going to go the opposite direction through my bright spot until I'm out of focus in the other direction and hit set last. Of course, out of focus is whatever that means for you and your sample. You may need the entire cell, you may not. Now in the Z-stack window, I have my first and last positions. Over here on the left side of the Z-stack, you can see F button is for first, C is for center, and L is for last. If I want to visit these positions, I can hit live again. I can hit F, and it will take me to the first position. And in this example, that's probably farther out of focus than I need to be, so I will bring it up a little bit and hit set first again and record a new position. I will hit C for center, and I will hit L for last and make sure this captures what I want. Now, importantly, you can see here that I traveled a range of 9.6 microns. You want to be sure to click the optimal button next to the word optimal. When I click 0.68 microns, it is now highlighted as blue. Let's talk about how this calculation was done. Up above, we can see that we set our pinhole so that our optical slice is 1.4 microns. The optimal way to do this Z step is to acquire 1.4 microns and then move up half that distance and do it again, half that distance and do it again. So that you will move up 50% each time, and that is the optimal way to sample by Nyquist sampling, oversample by Nyquist sampling. Thus, we will take 0.68, which is half of 1.4, divide it into the total range of 9.6 microns and come up with 15 slices. Now you can take a look at these numbers and see if they make sense for your particular sample. Is 9.6 the range that you expected? Is 15 slices a reasonable number? And you can make adjustments at this point. You could move your first and last slices up and down. You could adjust the number of slices, for example, from 15 to 10, and it will adjust the total range. So for this example, I will do that. We will take 10 slices. Once you are satisfied with your range and your first and last here, you have all of your tracks set. You are ready to acquire your image. One important point, if you have chosen sequential or best signal, you now have another option for how you can acquire this Z-stack. If we navigate back over here under imaging setup, it says switch track every, and we have a pull down menu. We've already made the choice to image by frame when we did the best signal, but we can now, for the Z-stack, acquire a full Z-stack before switching tracks. So in this case, this is a good choice. So, for example, instead of acquiring track 1, 2, 3, move in Z, 1, 2, 3, move in Z, we can now acquire the entire first track in Z, move, acquire the entire second track in Z, and so forth. This, most of the time, will improve your speed. So for this case, I'm going to switch track every Z-stack. And now I'm ready to actually start the experiment. Remember that we will now choose Start Experiment in the top left. And you can see that this full experiment only took between 10 and 15 seconds. So now we can come to our 2D or our split. Now, if you navigate to the bottom where we have our channels, we have a Z position slider. We can scroll through to the different slices that we acquired and see that we have different information on each slice. Now that we have spent time going through channels and each track one at a time, a reminder that this is how we will increase or decrease our signal for each track. Now we're going to visit all the settings up above under acquisition mode. Note, these are not settings that will actually increase or decrease your signal, and they won't truly affect your resolution, but these are ways that you can optimize your image a little bit more, change the size, and clean up your image a little bit. So we're going to walk through these one by one. First, we're going to show how we can do a crop or a zoom or a rotation to adjust our field of view. So this is the first thing under acquisition mode. If you are familiar with the previous version of Zen, this has moved. It was previously down at the bottom below channels, and it is now up here in the top left. We also need to be in our merge view to access the crop area. First, right below crop area, you can see scan area, and there's a small arrow. I'm going to open that drop down so that we can have more information and more settings. First, I'm going to hit crop area, and it will put a 2x zoom right in the middle of my screen. I can move this around to find a different area. I can grab the sides and rotate it. I could also grab the corners for a larger or smaller zoom. Note that you can see this number in the box. So for example, if I wanted a 3x zoom, I can type that in the box and the square will adjust. For now, I will stick with a 2x zoom. Note that this does not affect your signal, so everything we have done under channels is still fine. Under scan area, you can also see a small cartoon representation of what we've done, and you could adjust these numbers as well. So if you know you needed a 90-degree rotation or such, you can type numbers in the box. So now I can hit live and see the zoom that I have done, and you can see that I have adjusted my field of view. If you need to reset, you can reset scan area, and that will reset everything we've done here. And then next to the zoom, you could hit 1 and it would take it back to a 1x or no zoom. Below the crop or scan area, we can adjust our image size. So you can see here the actual size of the image, for example, 212 microns by 212 microns, but we have a frame size in pixels. The default is always 512 by 512, but we often would like a larger image. For example, if we come back to our image that we acquired just before, I'm going to uncheck the crop area, and I come to my 2D or even my split. I'm going to come to 2D, and I'm going to just look at the red. Down at the bottom where I chose the channels, if I hit 100%, this is the physical size of this image. It was only 512 by 512 pixels. If I want to zoom in on this after the fact, you can see that it will start to get pixely. So in this case where you wanted to do that, we would want to start with a larger frame size. So for the 512 by example, if we would like to increase this, just navigate to the right where it says presets, and there are many different presets available to you. 1024 by 1024 is often a good option, because you need to note that larger frame size equals much longer time. So you want to balance the time that it's going to take to acquire your image with the frame size that you need. There is also a button just below that says confocal. If you highlight the confocal button, it will adjust your frame size to the optimal or the maximal frame size without oversampling. Again, this can be a good option, in this case 1425 by 1425, but there are cases where this number is very large and would take a lot of time. In this example, we will stay with 1024 by 1024. The next section below that is noted as frame time, pixel time, or scan speed. The scan speed is how fast or how slow the laser scans across your sample. It equates to how long the laser sits on each individual pixel and is called pixel dwell time. So that is the number that you see here. By default, so far, we have a pixel dwell time of 0.51 microseconds. We can increase the scan speed, there's a max, or we can decrease. As you decrease the scan speed, your total acquisition time will go up, but it can also give a smoothing or a clean up feature to your image. There's a couple different ways that you can think about how to set your scan speed if you would like this clean up feature. You can either find the max scan speed and then back it off about two or three times, or you can set your pixel dwell time to be around 1 microsecond or more. So in this case, 1 microsecond would put us at a scan speed of 7. Note just above that, the frame time, 7.55 seconds. This is indicating how long it will take to acquire one frame. So in this case, one frame is the size that we have here, 1024, and it includes all 3 tracks. Remember that we have chosen best signal, which is the slowest option. Below this, we have direction, and you see 2 different options. You see an arrow going in the right direction, or you see an arrow going in both directions. You can choose unidirectional, the right facing arrow, which means that the laser will scan left to right, left to right, left to right at every line. Or you can choose bidirectional scanning, which means that the laser will scan left, right, right, left, left, right, right, left. So that saves time. There are rare instances where bidirectional scanning can give artifacts, but I believe that it is a good choice to save time and would try it for most samples. So you can see that our frame time went from 7 seconds to 5 seconds when we chose bidirectional. Finally, we have an option to average the imaging. So averaging takes the image once, takes the image twice, and mathematically averages pixel by pixel. Of course, if we average twice, it will take twice as long, but it can also give a smoothing or cleanup image because it will average out any background noise. Now, unfortunately, background noise is not autofluorescence or bad secondary or bad primary, but background noise could come from if your gain is a little too high or some other software issues. Just note, again, you will be hitting your sample twice or 4 times as much, so it's also hitting your sample with more light, and it will take longer. Okay, so let's revisit these one more time just to see what differences we can make in our image. So I'm going to start back here with our 512, with our max scan speed, and with no averaging. Okay, so with the default settings, I will hit snap. And it should take just under 1 minute. I can hit split, and here is my baseline image with the 2x zoom. Now I'm going to adjust these parameters. I'm going to change my frame size to confocal, which is 425 by 425. I'm going to adjust my scan speed to be 1.47 microsecond pixel dwell time. I have bidirectional scanning. I'm going to do an average of 2. So now we went from 1 second to 28 seconds. I will snap. Okay, now that we've acquired our optimized or adjusted image, let's take a look at some of the differences. We can look at our first image, 2D. We can look at our second image, and you can see that it is a much smoother image. Again, this is a decision for you to make as to where among these settings you want to fall for your particular sample and your post-acquisition analysis goals. Importantly, you want to think about optimizing your image versus your acquisition time. Also, I will note here is our 100%. This is the actual size of this image. and our larger image is obviously much larger, so we can zoom in a little better and see a lot more detail. Once you have acquired a Z-stack or a 3D image, there are some simple ways that we can visualize it in the Zen software just to see what we have acquired. For any 3D or 4D analysis, if you would like to learn other programs, please discuss with Scissor staff. We're going to just look at some very basic things in Zen. So as we noted, you have a Z position slider at the bottom to see the different slices that we have acquired. But then along the left in our vertical buttons, you can choose 3D. There's a couple different ways that you can look at your image. One is a maximum intensity projection. This will take our 10 slices and smash them down into one slice. So it is a 2D representation of a 3D image. It is a maximum intensity projection because it will look at every pixel, look through all 10 slices, find the maximum intensity, and that's the winning pixel, and that's how it creates the image. This can be good for some simple visualization. Maybe you want to look at microtubule tracks going in and out of the plane, or neuronal tracks, but you want to be very careful about analysis because things are not exactly where they were. You've taken the 3D image and compressed it into a 2D image. That's the default here under 3D, 3D tab below, and then maximum. If you would like to create this image, then you just click on the Create Image button, and it will open a new window that you can then save. Back to the experiment and 3D, we can also do volume. So just to the left of maximum, we have volume. And now we can move this around and see the 3D information that we have acquired. Again, this is kind of a quick and dirty volume rendering, but it's a good way for you to kind of take a look during your acquisition, your imaging session, to see if you're acquiring what you need. You can zoom in, you can turn your tracks on and off here as well. Again, you could create image and then save that if you would like. It will be a CZI image, and then you can export it. Another option you have along these vertical buttons on the left is the ortho view. This is an orthogonal view. We normally look at things in X, Y. This is a way we can look at our volume image in X, Z, or Y, Z. So for example, on the right-hand side, this small strip is looking at your sample in Y and Z. You can move these crosshatches around. For example, let's pretend like these little green dots are nuclei, and we can look and ask the question, is this single nucleus at the top or the bottom of the cell, or in this case, all throughout the cell? This can be a good way to visualize things that are pretty large in Z. It's very helpful for things like looking at junctions along the side of the cell, or other things, or looking at relative top and bottom images. Again, we have our orthogonal view. We can move these crosshairs around, and you can also move your Z position to the slice you want, and then down on the bottom you can create this image and save it. As you think through the settings for your acquisition mode, we discussed several of these things that will affect your time. So your frame size, of course, your scan speed, unidirectional versus bidirectional, and averaging. Of course, adding Z-stack with multiple slices also adds time to your final image. You can see here next to or above scan speed, it says frame time. This is an estimate of how long it will take to acquire this image. It includes all 3 tracks. It includes all the information here under acquisition mode. It does not include the number of Z slices. So for this example, 28 seconds times 10 slices would be 280 seconds. So you can get an idea of the relative differences as you adjust these settings. The frame time is not absolute, and I'm going to point out one example where it is definitely wrong. So if this is how I would like to acquire my image, I'm now going to hit Start Experiment. Once you hit Start Experiment, there will be a number in this box next to Stop that estimates how long it will take. You can see here it is 8 minutes and 39 seconds. Almost every time that you hit Start Experiment, it will start with 8 minutes and 39 seconds, and it is inaccurate. It will adjust over the next few seconds or minute to increase or decrease to give you an estimated time. Start recording, minimize. An important point about the reuse button when you're reusing settings from an old CZI image is that it will reuse almost everything but not all of your settings. 3 important things to note are the objective, your crop or zoom area, and your Z position. First of all, the objective, when you reuse, it will not reuse your objective. We have set it this way on purpose because we would like you to stop and think about which objective you're using so that we prevent any oil on any dry objectives. So my recommendation is, if you're going to reuse an image, is to open the software, open your old image, and reuse before you ever put your sample on the stage. So your workflow should be open the software, open your old image, reuse, choose your objective, and then load your sample. Another thing to remember about reuse is that the software will reuse your crop area and your zoom. It is common that you will be on a new sample, and so you generally would like to reset scan area and reset your zoom to 1 to find your new area. The third thing that you want to think about when you reuse an image is your Z. So for example, I will come to this Z stack and reuse, and I will get a message about reusing a Z stack. Reuse of Z stack positions may be risky. Do you want to center the Z stack around the current focus position instead? Yes, please choose yes, so that you are not choosing a Z position that is very far away from your sample. Every sample is different, and when you come on a different day with a different sample, your Z position will be pretty different. Once you have acquired your image, you often want to add a scale bar to your image. You can do this in the offline version of ZenBlue, which we will point you toward on our website, but I will show you here as well. Down toward the bottom, where we look at our display and channels, there is another tab called Graphics. Navigate to that tab, and then right kind of in the center is a little icon that looks like a ruler. Click on that icon, and it will automatically put scale bar and scale information on your image. Once it has populated the scale bar and scale information on your image, you can make adjustments. Note that you must navigate back to the 2D view to make these adjustments. I can highlight scale bar at the bottom, right click, format. Now I have a pop-up window where I can change the color of the line, I can change the font of the text, and I can change the color of the scale bar. If you want to increase the length of the scale bar, you can grab on the bar and drag it out to the size that you would like. Once you have acquired your images and saved them as CZI files, you often want to export them to a different file type, often TIFFs, for your downstream analysis. There is a quick and easy way to do this by batch processing here in ZenBlue. Navigate to the third tab called Processing. Next choice will be single or batch. We will choose batch. Like to export. Navigate to the folder under Add. Choose one or multiple images. Now under Batch Method, I will choose Image Export. And then below, I will have several parameters to choose. For file type, I will choose TIFF. Next, I will choose no compression. Then below, I want to uncheck burn in graphics. We don't have graphics on these images, but you want to make sure that you remove them for your downstream analysis. Below that, we have two boxes to check: merge channel images and individual channel images. This is good because then you'll get your image that has all three colors or four, and you will have each one individually for you to use as you need. At the very bottom, you'll see create folder. So for each CZI file, we will now have a folder that has the individual and the merged channels. If you did a tile scan or a Z-scan, you would also have an individual for each one of those. Right here, we will use full set of dimensions, but there could be situations where you want to define a subset. Maybe you don't want all the channels or all the Z positions. You could choose that here. We will use full set today. Now I will navigate and you can see that the first one has all the parameters that I have set. However, it did not populate for all the other files. So for the first one, I will highlight and click copy parameters. Now I will shift and select all for all of the files and hit paste parameters. It will also change to image export. At the top, the default should be use input folder as output folder. And then on the left, we will hit apply and you will see the export happening. You can now navigate to your folder to see the subfolders with your individual and merge files.